In the next couple of lecture videos, I wanted to talk about radical expressions, how to simplify, multiply, add, subtract, all the properties of dealing with roots of different forms. And to begin with, it's helpful to talk about some of the simplification properties for how radicals work. So the first couple properties are ones you may be familiar with, but basically if we have a product or a quotient of two radical expressions, assuming that the index is the same, what will happen is we'll translate to a direct product of the two interior components. So, let's say for example, I had the square root of 2 times the square root of 3. That would simply make the square root of 2 times 3 all within a single square root, which would be equal to the square root of 6. While that may or may not be rational, it's a way of dealing with multiple ones and combining together. And in the same way, you can also take a square root and break it down into parts if you need to. That's one of the key ways that we can actually simplify a radical. Like, for example, say we had the square root of 20. Since 20 is equal to the square root of 4 times 5, we could actually break that down as the square root of 4 multiplied by the square root of 5 separately. And since 4 is a perfect square, that would make 2 rad 5, and we often refer to that as simplifying. We'll do more examples of that in a later video. And the same rule applies towards all indexed roots, but it's worth mentioning that in these cases, these only work for numbers a and b, which are positive, because if they're negative, those components would be not real to begin with, and actually these rules don't work anymore in those cases. The same thing goes for a quotient of some square roots, like say for example I had the square root of 12 divided by the square root of 3. I could simplify that simply by taking the quotient square root of 12 over 3 all in a larger square root, which would just be the square root of 4, in that case making 2. And sometimes it can be very easy to simplify roots by using these properties. And the cancellation properties we actually discussed in the last module. But basically, it's whenever I have an nth indexed root applied to x to the nth power, those will cancel each other out. Assuming that the index is odd, it will cancel directly, but in the case when we have an even index root, it will always produce a positive number, which was the need for the absolute value. So, say for example, we had the fourth root of 4 to the fourth power. That would be the fourth root and the fourth power would cancel, leaving us with the absolute value of 4, which is of course 4. But anyways, let's look at a few other examples. So, what you could be asked to simplify some sort of product or quotient of different roots, but basically you could simplify them in parts to begin with, but you could always begin by multiplying them together if you want. So like for example, 54 times 6 is just going to be 324. So in this case, we could evaluate this by taking the product of those two things, which is root 324. And then you may or may not remember what the square root of 324 is, but we could always just evaluate with our calculator. And as we talked about in the last video, square root is equivalent to the 1/2 power, so I could figure it out that way, which would leave me with 18. Or, in a similar fashion, say the square root of 8 over 2, or over the square root of 2, that would be equal to the square root of 8 divided by 2 together. And that would leave me with the square root of 4, which is again indeed 2. Of course, you could use a calculator and just do the square root of 8 divided by the square root of 2. But what's the fun in that? And similarly for cube roots or fourth roots or any nth root, same thing holds. So say I want to do this cube root of 2 times the cube root of 32, that would be equal to the cube root of 64. And that's just going to be 4 because 4 to the third power makes 64. Or if I had the cube root of 81 over 3, that would just be equal to the cube root of 81 divided by 3, which is 27. And then the cube root of 27 is just 3. So many times, depending on the numbers, it may simplify or it may not, but those properties are quite important. So kind of like what I was saying before, we can actually simplify radicals by applying this property in reverse. So like looking at a particular set of these numbers, if I wanted to simplify them, I could always start by factorizing the interior and using that factorization to break them down into parts. And the key that I recommend here is to look for perfect square factors within the radicals if you can. So meaning I'm looking for numbers like 4, 9, 16, 25, 36, so on, because those numbers have a direct square root when it is a perfect square, and it will cancel. But like in the case of 72, 72 is 36 times 2. And the reason why that factorization is helpful is because 36 is just 6 squared. So if I were to break this down by property number 1 above, this would be square root of 36 times the square root of 2. And the square root of 36 is, of course, just 6. So essentially, simplifying the radical means making the radicand smaller by breaking it down into parts that I can take the square root of, doing so and rewriting it as this. And it's worth mentioning that when you write something like this, this means 6 multiplied by the square root of 2. It's only the 6 root when it's small and above. So those are not the same thing. And, you know, just like with algebra, if we say 3x, it always means multiply when we have them written like this. If we wanted to add them, you would have to put a plus symbol in between them. So like the square root of 8 is another pretty common one. Since 8 is 4 times 2, we could factor it as such. And then usually we skip the step where I just say, well, the square root of 4 is 2, and I could just rewrite this as 2 root 2. Essentially, it's kind of like extracting the perfect square out and taking the square root of that component as I go. But again, it's all predicated on this product property of the square roots. And looking at another one, say 150, how you'd probably think to factor this first would be 10 times 15. The issue with that is that 10 and 15 are not perfect squares. So I could kind of think about, well, between those two numbers, is anything in common? And actually what has become common between 10 and 15 is 5. So actually, notice that, well, this is really 25 times 6. And the reason why that's the way I'd want to break it down is because 25 is a perfect square, meaning that I could actually simplify that component into a whole number. And we'd say that 1 square root of 150 is equal to 5 root 6. And again, we refer to these sort of answers as simplified, just because the inside is getting smaller. And it's important that it's equivalent. If you're not really sure if you're doing it right, you can always check your calculator by seeing, well, what is the square root of 150? That approximates, again, it's irrational because it isn't a perfect square, but it gives me something, about 12.2 approximately. And I could also check 5 root 6 and say, well, make sure it's the same. That way I know that I'm simplifying these correctly.